I am Snigdha Bharadwaj, Assistant Professor, ITS College of Pharmacy. I welcome you all in my session. So, in our last session, we have started reaction kinetics. So, and we have discussed basic fundamentals of reaction kinetics and factor affecting rate of reaction. In this particular session, we will be talking about rate laws, reaction orders in detail. So, let us get started. So, basically reaction kinetics in chemistry, the amount unit may vary, but it is often in moles. So, in our last lecture also you must remember, you must have remembered that we talk about concentration in moles. So, in chemistry moles per liter, moles and molarity, grams or even liters, we usually analyze the concentration in these units. So, rate of chemical reaction are most often measured as mole per second, molarity per second, because the rate is giving you the value per unit time, right, the concentration change in concentration per unit time. So, reaction kinetics basically are analyzed with these units like moles per second, molarity per seconds. So, first we will talk about rate law. So, for any general reaction occurring at a fixed temperature like A. So, in our last session these small alphabets represent the coefficients value, right. So, for product A, so A will be coefficient in the reaction. For product B or reactant B, so A plus B. So, these are reactants and will give you the product C and D. So, along with that coefficient values are there. So, the term K is the rate constant, rate of reaction. So, it is a constant basically which is specific for a given reaction at a given temperature. So, basically the rate of reaction is very specific at the temperature it is getting reacted. The exponents m and n are, so basically it can be represented as rate is equal to K, rate of reaction, reaction constant basically A and B, m and n. So, these are exponents m and n are reaction orders. So, orders. So, generally how much number of reactants are participating with each other in a particular reaction will give you 0 order, first order and second order respectively, right. So, these exponents are m and n are reaction orders and are determined by experiments, right. The value of m and n are not necessarily related in any way to the coefficient A and B. So, it does not have any direct relationship with the A and B, these are the order of reactions basically. So, reaction orders. A reaction has an individual order with respect to or in each reactant. For example, if one substrate are participating in a reaction in order to give a product, that means it is following first order reaction, right. So, the reactant's concentration is independent to the rate of reaction or giving the product end product, that is considered under 0 order kind of reactions. So, basically for the simplest reaction A will give the product. So, if the rate doubles when A doubles, the rate depends on A and the reaction is first order with respect to A. That means, the product concentration is depending on the concentration of A will give you the first order reactions. If the rate quadruplus when A doubles, the rate depends on A to the power 2 and the reaction is second order with respect to A. So, 2 times doubles the rate depends on the, so if the rate when doubles the rate depends on and the reaction is considered to be second time, second order reaction. So, this representation is the first order with respect to A and quadruplus 4 times and the reaction is second order. So, 4 times increasing the rate. So, that will be like second order reaction. If the rate does not change when A doubles, right, the rate does not change along with its concentration, that means the reaction is 0 order with respect to A. So, if it is getting doubled and the rate depends on the concentration of this particular A. So, that means it is first order reaction. If it is like depending on this value, the rate will be second, quadruples, and second order reaction, if it is the rate does not change, rate does not change depending on this A concentration, the reaction will be considered as zero order reaction with respect to A. So, determining reaction orders for the general reaction A plus 2B will give C plus D. If we say that this is the reaction of any particular product, the rate law will have the form, what will be the equation to do as per the rate law, rate is equal to K, this is the rate constant, and A is the value A and B plus M and N. These are what we say it exponent, these are exponent which is giving you the information about reaction orders. So, basically this is the equation generally followed during this simple general reaction. To determine the values of M and N, we run a series of experiment in which one reactant concentration changes while the other is kept constant, and we measure the effect on initial rate in each case. So, generally to identify the values of M and N, that means specific reaction orders. So, we generally run a series of experiments to analyze which type of reactant is changing and which is kept constant under particular temperature, or we can say pH or any kind of particular specific conditions, right. So, although we have different reaction conditions for different kind of substrates, but how we can determine the reaction orders, we generally run a series, and now we observe how much reactants are participating in a particular reaction to get the desired product. So, graphically it can be like series of plots of concentration versus time. So, concentration change basically with respect to time is the rate of reaction. So, for identifying the rate of reaction or order reaction orders, we generally run a series of experiments, initial rates and reaction orders, and then rate constant and actual rate law. So, this is the hierarchy we follow for identifying. So, determine slope of tangent at t 0 for each plot. So, basically we are taking that time and concentration. So, concentration and time. So, generally if we talk about this point is considered as t 0 and t 1. So, compare initial rate when A changes and B is held constant. So, for example, at point something we can say at A and B we say. So, as the time proceeds, A is getting increased in terms of product and B is kept constant at this particular change rate. So, we can say vice versa. So, substitutes initial rates, orders and concentration into rate, and we can put the values we are getting from the experiments and solve for K. So, we can identify K using the concentration change at particular time, and we can put these value to identify the constant rate, right. So, information sequences, these are the information sequences to determine the kinetic parameters of reaction. First, we run a series of experiments, then initial rates identify, and then reaction orders we must have to be put in this particular equation in place of M and N, and then rate constant and actual rate law, right. So, finally, in order to analyze that rate constant, we follow different parameters to be measured. So, units of the rate constant K for several overall reaction orders. So, what are the basic units? So, overall reaction order, like we have said that 0 order, first order, second order and third order. So, units of K, T in seconds will be like mole, per liter dot as seconds basically, or mole liter minus liter inverse second inverse. So, this can be represented as this also. Unit of K can be like L liters per mole order minus 1 unit by time. So, this is the order we generally it is following, the reaction is following. So, we can put the values to identify the rate constant of a particular reaction. So, order minus 1, that means if like order minus 1. So, this has to be put here. So, first order is like 1 by second or second inverse, second order units of K will be in L by mole per L by mole second, and third order reaction in third order reaction units of K in T in seconds. Basically, we are taking time in seconds, not in minutes. So, liter square by mole square into seconds. So, the value of K is easily determined from experimental rate data. The units of K depend on the overall reaction order. So, basically the K for first order reaction, the unit will be like this. If 0 order reaction is there, the unit of K will be this. So, these are the units of K we have for different reaction orders. So, now after talking about rate constant values, we talk about 0 order reaction. So, in 0 order reaction, the reaction rate is independent. That means, it does not depend on the concentration of reactant present in the participating in the reaction. So, in 0 order reaction, the rate reaction rate is independent of the concentration of the reacting substance on reaction rate on the 0 power of the reactant, right. So, example, degradation of solution when solubility is the factor, only the amount of drug that is in solution undergoes degradation. Basically, when we talk about the overall concentration, so if we say that drug is getting degraded in the solution form, that means we are saying the solubilized type of drug is getting degraded when present in solubilized. The non-solubilized drug will not get degraded. So, this is the relationship T x is the concentration, T is the time. So, K q is the 0 order coefficient or rate constant. So, first order reaction, as the name suggests, the rate depends on the concentration of one reactant. The rate equation is dx by dt basically is the rate of reaction K 1 A minus x. So, x is the concentration. So, integrating this equation with respect to time from T 0 to T t. So, at time 0 the reactant concentration will be much higher at the time t, because it is now getting changed to that particular what we say product. So, this equation will be followed K 1 2.303 divided by T log A minus x, where A is the amount of drug, where A is the amount of drug degraded at time t, x is the initial amount of drug, K 1 is the rate of reaction. So, basically K 1 is the rate of reaction, it is the concentration degraded initially, and now where A is the amount of drug degraded at time t. So, it is a initial concentration and the degraded concentration at time t. So, the how we can this is how we can calculate the reactant's concentration changing or degrading during the rate of reaction. So, rate of decomposition of a drug A is the change of concentration of A over a time interval T, that is minus d bracket square A by dt. So, note that this is a negative value because the drug concentration is decreasing. Yes, we are saying that drug is getting decomposed, that means the drug is degrading from its pure form. Now, the negative signs represent that its decomposition as the time increases. It is, however, it is more usual to express the rate as dx by dt, where x is the amount of drug which has reacted in time t. So, x represent the concentration or the amount of drug generally we do not say amount when we measure the rate of reaction or any kind of reaction, we say the concentration of drug participated in the reaction. So, so x is basically amount in terms of concentration which has reacted in time t. So, this is how we usually identify first order reaction using this formula, and it depends on the concentration of one reactant. So, first order reaction basically it is a rearrangement of the previous equations gives. So, if we rearrange the previous equation, we can have T is equal to 2.303 K 1 log A 2.2 minus 2.303 divided by. So, this equation log A minus x. So, when we rearrange the equation, so we can have this type of plot. So, log A, this is concentration, this is time. So, this is the slope representing the value of minus 2.303 K 1. So, comparing this equation with y is equal to m x plus c. So, basically x is the amount of a concentration of drug, m and c are the constant value, and y is your absorbance, and rate of reaction means we can say a plot of time t versus log A minus, we get this equation. If we compare this equation with this, so we at the end we can get this slope value. So, slope will give you the value of the concentration of the reactants reacted in a particular type of reaction. Now, after first order kinetics, second order reaction, as the name suggests, the rate depends on the concentration of two reacting species like A and B. First order depends on the reacting species 1, whereas in second order reaction it is usually depends on the two reacting species. For the usual case where the initial concentration of A and B are different, the rate equation will be like dx by dt K 2, because 2 represent the two different reactants participating in the rate of reaction A minus x, B minus x. So, this is for one component reacting component, and this is for second, where A is the initial concentration of A, B is the initial concentration of B, right. So, these are the values which represent initial concentrations of both the reactants, and x is the amount of drug decomposed or changed during the reaction. So, basically x is the value. So, it will give you the variation or change in concentration level. So, x is the amount of drug change, and these are the initial concentrations of A and B. So, now you can easily identify the we can say the concentration at or rate of reaction. Second order reaction, basically integrating this equation with respect to time. So, at time we generally take these values at different time intervals. So, at time 0 and time t, when we expect that all the reactants interacted with each other to give the desired product. So, we can say we can take this equation to identify K 2 second order reaction 2.303 T A minus B. This is the log value B A minus x and A B minus x. So, rearranging this equation with the particular this equation, we can, this is the basic equation, we can have we can put our second order reaction and 2.303 K 2 A minus B log B divided by A. So, comparing this equation y is equal to m x plus c. So, we can have this slope value 2.303 divided by K 2, because we are calculating rate of reaction for second order type of reactions. So, A minus B. So, basically K 2 second order A minus B slope represent the this type of this T, and this is the concentration change log A minus x B minus x, initial concentrations and the drug changed or degraded. So, by taking the difference amount, we can have this type of slope in a particular, when we plot these values, and this type of plot we can have for second order reactions. So, rate versus time graph. So, I have rearranged all the graphs in terms of rate and concentration. So, this represent the rate does not change for zero order reactions. So, you can see that this is constant, right. When we see that when we talk about first order reaction, so rate basically depends on the concentration of one component or reacting species, and in second order it depends on the two reacting species. So, we will get the increased rate of reaction, a curve line. So, this represents concentration and rate. So, concentration does not have any effect on the rate of reaction in zero order type. Basically, first order and second order is a direct relationship. So, rate of reaction will be higher when the components react with each other. So, concentration, when we talk about time and concentration. So, zero order have the concentration this type of graph curve, and first order this, and second order also slightly curve. So, these are different representations. When we do the experiment, we will get this type of representation when while putting our experimental data to get the desired rate and concentration time profile curves. So, pseudo order zero order reaction, it is also order. Many drugs in the solid state decompose according to pseudo order rates as a reaction occur between the drug and moisture in the solid dosage form. So, pseudo order rate, basically pseudo is a false, we can say in general terms. So, pseudo order rates reaction occur between the drug and moisture in the solid dosage form. The system behaves as a suspension, and because of the presence of excess solid drug, the first order reaction becomes a pseudo order pseudo zero order rate, and loss rate is linear with time. So, in some cases while we identifying for reaction rate for several dosage form. So, pseudo zero order reaction occurs between the drug and the moisture in some sort of formulation, for example, suspension, solid dosage form. So, what we in the equation we follow, R is a dCA by dt K1 Ca. In suspensions, the concentration of D, the aqueous phase remains constant, that is saturated until the suspended drug particle are completely exhausted. Basically, in suspension the drug concentration, the aqueous phase remains constant, that is saturated until the suspended drug particles are completely exhausted. So, during this using this equation we can identify pseudo zero order reaction kinetics. So, first order pseudo first order reaction kinetics of pseudo first order reaction can be defined as a second order or bimolecular reaction that is made to behave like first order reaction. This happens when one reacting material is present in great excess or is maintained at constant concentration compared with the other substance. That means, if one reactant is present in major proportion in the reaction, and its constant and maintain and constant concentration, that means concentration is not gradually increasing with as compared to other substance. In that case, pseudo first order reaction generally follows. Under such circumstances, the reaction does not exhibit a significant change in concentration, because the concentration is kept constant during the reaction. So, during the degradative reaction. So, these type of reaction generally follow pseudo first order reaction. Example, hydrolysis of an ester. The drug that obeys pseudo first order kinetics is cefotaxime sodium. So, this is the example of pseudo first order reaction. Now, integrated laws. So, when an integrated law includes time as a variable. So, these are the different representation of equations. So, first order, basically we use this equation, rate minus delta A divided by delta T. So, these are the change in concentration and change in temperature. So, by simplifying these, so for second order we have this much this type of equation, and for 0 order we have this A square bracket T minus A. So, at time 0 and at time t the representation will be like this. So, graphical methods we say when we although we have discussed earlier, but integrated like log values. So, integrated log so slope will be like minus k for first order, time and integrated amount. This also represent the concentration change for first order. This is for second order. The slope is like downwards for the first order reaction, and this is the representation of second order reaction integrated law as per integrated rate law. And for this 0 order, at 0 order, that A 0 represent the order type of a reaction. So, these are integrated, and now reaction half life. The half life T for a reaction is the time taking for the concentration of reactant to drop half of its initial value. So, when how much time reactant is taking to reduce its half to its initial value. For first order reaction, T half does not depend on a starting concentration. The formula will be T half is equal to integration to K, and the value will be 0.693 divided by K. The half life of for a first order reaction is constant basically. So, radioactive decay is the first order process. The half life of a radioactive nucleus is useful indicator for its stability. So, generally half life first order in first order type of reaction is constant. Half life equation for second order, it is like inversely T half 1 by K. Second order process, K the final value will be K bracket A square. So, for 0 order reaction, T half is directly proportional to the initial concentration. So, this equation represents the half life for second order reaction, and this equation represents the half life for 0 order. So, using these equation we can calculate different kind of orders. So, basically an overview of 0 order, first order, simple second order reaction. Rate law will be like this: representation units K, mole, second. So, rate constant, half life can be presented. So, this table represents what we have discussed earlier in the session. So, these are references. I hope you understand all the basic rate laws and reaction orders, and why they are important for identifying different kind of parameters in reaction kinetics. So, in our next session we will be discussing with the same topic. Till then, take care and stay safe. Thank you.